All right. Okay, so recording's rolling still, recording rolling. All right. So let's start with maybe a projectile type question. So like kinematic motion. They got a edge of a table. Here, I can do the 3D. How about that? Okay. And I got a couple of maybe like baseballs. How about that? Right. And one of these baseballs, I'm just gonna let roll off the edge, just like pretty much plummet straight down. Okay. Uh, let's have let's say I don't even tell you the mass of the ball because let's just stick to kinematic motion. You guys remember kinematic motion? We never even really care about the masses or forces, right? We're just looking at position, velocity, acceleration, time. Right? Let's give this a height of 3 meters. How about that? Okay. Okay. In this other ball, let's kick off horizontally with I'll say v sub x. Right, help you guys out a little bit. Right? It's gonna be horizontal component velocity. Let's say 5 meters per second. Right? Now, a good assumption is that we're on Earth, right? So let's use gravity equals about 10 meters per second squared. Right? And this is going to go into projectile. This is your point. Right? Land some distance away. Right? Maybe I'll call this distance d. Right? There could be some distance d that it goes. Okay, like I said. All right. So let's ask questions about these two scenarios. Right? Let's start figuring out what is that distance d? What is that distance d? Okay. You guys solve it. I'll solve it off screen, and we'll see if we get the same thing. All right. Let's see. Show hands. How many guys got the answer by now? Who's got it? All right. What do you got?
3.7
Oh, okay. 3.87, and the unit is
meters.
Meters. All right. Okay. Thanks. What I got too. How many guys got about that? About 3.87 meters. Okay. Yeah. I'm seeing some hands. All right. Nice. Okay. So, wait a minute. What about this is well, how far it goes depends on okay, well, how fast it's going across, but also like what is the time of fall? And the time of fall depends on the height that it falls and also the gravity field of the planet. So I'm actually going to start with that. I'm going to start with vertical motion so I can figure out the time of fall and then switch over to horizontal. All right, let me and so h is 1/2 gt squared. You could say v naught t plus, but if you throw it off horizontally, that v naught in the y direction just goes to 0 anyway. So solve for t. Well, t squared, that's 2h divided by g, square root both sides. Right. Okay. So there's a general expression for t in terms of variables. Right. It's a good skill to be able to do that. Can you guys solve in terms of variables? Right. Right. You guys see that? Right. You can plug in the numbers whenever you want. I went ahead and saved that for the end here. Right. 3-meter height drop, 10 meters per second squared gravity field. Got that's many seconds time fall. Okay. Right. Okay. Once you know the time that it's been falling for, you can go ahead and switch over to horizontal motion to figure out how far it went horizontally. Call this horizontal displacement. That's that d we're solving for. So that's how fast it's going across the field times however much time it was falling for. Right? Time was a projectile for. Right? So I told you guys 5 meters per second is going across. Right? Remember that's fast across. Right? And for this much time. Right? 3.87 meters. There you go. Okay. Now, AP usually rounds to two significant figures, so I'm guessing their choice would be like 3.9 meters. That's what I'm guessing, right? Or they might even do something like, what's the closest answer? And they'll have like 1, 2, 3, or 4 meters. You say, okay, well, it's closest to 4 meters. Right? Yeah.
On an FRQ, how should we round it?
If you do 3 digits, that's probably what I recommend. Is like 3 digits. Yeah, yeah. So FRQ, right? And then they'll give you like a little bit of a window. So yeah, so FRQ, I would write 3.87 meters. Okay. If you do 3.9 meters, they should take that too. But, okay. All right. Let's do a follow-up question about this. What is the crash speed here? I'll call this. Here, let's do a little fatter here. Okay. I'll call this V sub A, okay, versus this crash speed here. Kind of on a angle. I'll call this V sub B. Right. Can you guys solve for those two crash speed? Before you go solving, guys, which crash speed is going to be greater, A or B? It's B's got to be greater than A, right? Okay. So you guys go ahead and solve that. I'll solve it off screen and see if we get the same thing again. Okay, how many guys need a little more time? A little more time. Okay, yeah, one more time. Go ahead. All right. Let me see what you guys got. What'd you guys get for V sub A? 7.75 meters per second. There you go. Right. Oh yeah. Guys, on your FRQs, you're gonna label all your units, right? Right. You're not just gonna have like naked numbers, right? You guys are gonna have units. Right? What'd you guys get for V sub B? Boom. All right. Scott got both of them. 9.22 meters per second. Who else got 9.22 meters per second? All right. Letch got it. Ruby got it. Okay. All right. Nice. Okay. So here, show you guys a couple of ways to get the 7.75 meters per second for V sub A. Right. you guys remember this one? VF squared is V naught squared plus 2AX, right? And if you just drop it, then the V naught goes away anyway. Right? Right, so the V final is square root 2AX. Hey, does that look like square root 2GH? Which also reminds me a lot of conservation of energy, right? Kind of leads to the same outcome, right? But we got this gravity field, we got this height drop, right? So we got 7.75 meters per second. Right? Or you could have done it this other way. You could say, hey, I already know how much time it takes because we just solved that before. So I can just multiply it by the gravity field, and it gives me the same answer, right? Right. V equals V final equals V initial plus GT, right? And then V initial is 0 again. Right? Right. Guys, remember that? All right. So that's that. Now you can actually use this to help you answer the second question because this crash speed, right? Because this crash speed doesn't it have both a horizontal component and a vertical component, right? In the vertical component, we just found, right? However fast it's crash landing strictly vertically is the same regardless of whether you drop it or throw it to the side, right? So we just got that, right? Two different ways, I'm sure. Right? And the horizontal speed was given in the premise. Guys, can you do Pythagorean theorem with velocities? Yes, you can. And that's exactly what you do. This is Pythagorean theorem right here, isn't it? Right. This squared is the square plus the squared. I just skip a step into the square root. Right. Right. And there you go. 9.22 meters per second. Okay. All right. Are we good? All right. Who got a question? Any question? All right. Let's try. How about a unit 2 question here? All right. Suppose I got a a box. Right? And let's say between this box and this floor, right, there is a coefficient of kinetic friction of like 0.3 and a coefficient of static friction of like 0.4. Right? And this box has a mass of let's say 10 kilograms, right? And somebody's pushing this box, right? With an applied force, I'll say a force applied, right? And let's say it's just strictly horizontal, right? So they're pushing to the right horizontally, right? Of, let's say 50 newtons, 50 newtons of force, okay? Okay. And yeah, let's do even a kinematic connection here, right? Let's say that there's a wall right here, and this distance to the wall, or let's go from the surface to the wall, right? With that, right? I'll say this distance is like 12 meters, right? And the question is going to be how much time to push the the box to the wall, right? Right, you guys get that? Right. Question so far? Question. Right. All right. Okay, so we got here, giving you guys kind of hint here. It's gonna be unit 2 and unit 1, kind of a mix. Okay. Here's what I do. I'm gonna freeze this, and then I'll just start solving it here. Okay. So if you're watching this video at home, I'm just starting on the solution. But if you're at home or in my classroom right now, you just see everything written so far. Oh, I should have said starts from rest. Is that okay if it starts from rest? Okay, so it starts from rest. Show of hands. How many guys got the answer? Okay. Other guys, you need a little more time. A little more time. All right, you guys ready to see the answer? Ready to see it? What'd you get?
Is it 3.46?
Okay, that's right. 3.46 seconds. That's what I got too. 3.46 seconds. Right. So let me unfreeze this. Okay. So I just unfroze it. So again, if you're in class, you haven't seen my work yet, but if you're watching the video at home, then you just saw the whole thing work out. So I made a free body diagram on this blocks. Guys, it has a weight of how many newtons? 100 newtons, right? With mass 10 kilograms, it weighs 100 newtons. The normal force from the floor, 100 newtons. Right, is that right? The applied force is 50 newtons. I told you that, so I just went ahead and drew it there. You guys see how all my vectors are connected to the central dot, right? I've seen AP graders tell me, even if your vector is not connected to the central dot by like 1 meter, if there's a tiny space, they will not count it. I guess like that strict. So make sure all your vectors connect to that central dot. And then there is a friction force. Now, guys, friction, let's kick over to friction is coefficient of friction times the normal force. Now, it's true as long as it's kinetic friction. And the fact that the pushing force will be overcoming the friction force anyway. I just went ahead and used coefficient of kinetic friction, right? So the normal force is 100 newtons. The coefficient of kinetic friction is 0.3. Put that together, 30 Newton friction force. You guys see 30 Newton friction force? Is that okay? All right. So we got all our forces. Now, the question is how much time does it take to reach the wall? That's the kinematic question. Hey, guys, what variable connects unit 2 dynamics to unit 1 kinematic motion? Acceleration. We got to find the acceleration. And how do you get acceleration starting from dynamic information?
By mass.
Force divided by mass, right? Net force divided by mass, right? Is that Newton's second law? Let's bring up Newton's second law of motion. Here's Newton's second law of motion. Net force on mass. Now, careful about net force, because now the vertical stuff just cancels out. But the horizontal stuff, there is a net force. You got 50 newtons pushing and 30 newtons, like a drag force, friction force, right? You have to subtract those two, right? Isn't like a 20 Newton net force, right? Acting on a 10 kilogram box. 20 newtons acting on 10 kilograms, that's like 2 meters per second squared. Right? You could also call that 2 newtons per kilogram. Sometimes they write the answer that way. Okay, so there's the acceleration. Now we got to get back over to unit 1 kinematic motion. We know the distance to the wall. We know the acceleration. The question is the time. Which equation is this going to be? The first one, right? So in the stripped down version of it is distance is 1/2 AT squared. Can we do that? 1/2 AT squared? Right. All right. You guys got that? All right. So again, just like a last question, I solved in terms of variables. So the time is, let's see, 2 times the distance, divide by the acceleration, take the square root. Okay, that's how much time it's going to take. Okay, and we have those things. So the distance was 12 meters. The acceleration we calculated 2 meters per second squared. Pop it in, 3.46 seconds. Right. Okay, if this was a multiple choice question, I'm guessing that they would say it's 3.5 seconds. Thanks, Scott. Okay, you guys good there? Guys good? All right, let's do. All right, you guys ready for a unit 3 type question? Unit 3. Okay. Let me ask you guys a real classic unit 3 type question. Let's say, and I've asked this over and over, so you guys gotta get this by now. Okay. Suppose there's a planet that has mass m, right? and there's a satellite with mass little m, and the satellite is in a circular orbit. That's pretty much a circle right there, right? Circular orbit around that planet, and it's way out here. It's way out at distance. I'll call it lowercase r. Right, you guys see lowercase r? It's way out there. Oops, that's straight there. Right, and then at that distance right there. Okay, right, you guys see that setup? I want to know how fast do I have to get this going? Like a tangential speed, I'll call it v, or maybe just call it v orb, like an orbital speed, so that that satellite stays in circular orbit around that planet. Right? This is all in terms of variables. Right? So giving you guys a head start here. All right, let's start going through the solution. Hopefully, some of you guys got this by now. If you want, remember, might be a good idea actually to memorize the solution, maybe since we use it so much. But if this is an FRQ, they'll expect you to solve this from scratch. And what should your first step be?
The gravitational force equal to the centripetal force.
Exactly, right. The centripetal force is provided only by the gravitational force. In fact, if I do a free body diagram on this satellite, isn't there only one force on the satellite? And it's weight pulling that way, right? I'll call it F sub G, right? And then, oh guys, is there an equal and opposite force pulling the planet back towards the satellite? Also F sub G, right? But the planet is so massive that its motion from that force is negligible, but the satellite has such small mass that it's going to go into orbit. Okay. Right. So, but they are equal forces. Okay. What was the expression for centripetal force?
V squared over R.
mv squared over r. Exactly. Right. Now on your AP equations, you guys know your they're gonna give you this. Right? Actually, it's double-sided. They got this on the other side, right? Got some constants and some trig identity, some prefixes. Okay. But we usually focus on the side. They don't exactly give you that one, but they give one really similar. Point out right here. It's kind of near the top. It says centripetal acceleration is v squared on r. Well, you guys know force is mass times acceleration. So if you just throw a mass in there, then you got centripetal force, right? Okay, so now we're back to that right there, right? So it's good to know that one, have that in your back pocket. And that is provided by, remember, centripetal force is never just a force unto itself. There's always either some force or some combination or net force that's providing that circular type motion. So what is this one right here? There you go. G M M on R squared. Right, you guys remember that too? You guys remember that? Right, everybody gets so far? Okay. Now, what cancels out both sides? Yeah, the mass of the satellite. So if you had a satellite that was like 3 times as massive, is the answer gonna change? No, same answer, right? Right, we're like solve for this V. Like, what is that orbital speed? Right. Oh, one of the R's cancels too, right? Right. Hey, I can just square root both sides of this part, couldn't I? That orbital speed, that's what that is, the orbital speed, is square root G M on R. Okay. Again, you guys have seen this enough times that you've probably memorized this by now. Okay, yeah. Okay. Next question. What if, because one thing AP likes to do is they like to change variables around and say like, you change this variable, how does that affect something else, right? What if you had a planet that was 4 times the mass, right? 4 times the mass, but you left the same distance from the center, the whole deal, right? 4 times the mass. What would happen to the orbital speed? Double, yeah, right? Because you factor 4 there is like 2 times here. Right? If that's the same, right? So you could write out the way you do it is you'd say v, maybe I'll say 2, like the new orbital speed, right, is square root G 4m on R, right? And then you can take this 4, it's under the square root, so you pull it out front, and you get 2 times the square root of gm on R, which is 2 times v orbital, that's twice the speed. Okay, it's kind of like a way you could prove that. Right. What if, fuck that idea. Right. What if you backed this satellite up to 4 times the distance far away from the center? 4 times the distance. What happens to orbital speed? Half. Yeah, it's half the speed, right? You get 4 times far away, you have half the speed, right? Just 1 over the square root of 4. Okay. Right. One more question. What if you have 4 times the mass of the satellite? Right? It gets a huge supply load, right? So just got a bunch of new supplies. Hey, I got 4 times the mass of the satellite. Now what's the new orbital speed? The same, no change. There you go, right? Because the mass of the satellite is not part of this expression, right? Okay. You guys got that? Right. Let's do unit 4, conservation of energy. There's a real classic conservation of energy question I like. I even made a poster for this one. Right. Suppose we got a spring, a block, mass m. I'm going to compress this some distance x and let it fly. And at some point later in the system, it's going to be at the top of the track going around. Some speed v at the top, right? And there is a minimum speed it has to get around, but let's say it gets around with sufficient speed, right? It's not in danger of falling off the track, right? Let's have this height change as like h, and what else do we? Let's say no friction. Okay, so same block here. Okay. So, I want you guys to set up a conservation of energy expression that could solve for the speed of the block at the top. Set up a conservation of energy expression that could solve for the speed of the block at the top. Oh, I guess I should ask you guys too. If it's a conservation of energy, we're assuming a closed system. Guys, what is in the closed system? Oh, okay, yeah. So we got the block for sure. It's changing its speed, so we care about the block. We care about the spring because there's energy stored in the spring to begin with, right? And then that's where the energy is coming from. The Earth, because there's a height change, right? So the Earth is doing work on the block. I guess negative work, right? Now, should you include the track if there's no friction? Right, not if there's no friction. Right now, if there is friction, then there could be a frictional force. You have to include the track. But if it's frictionless, then remember the motion of the block and the normal force from the track are always perpendicular, so there's no work done. So you can go ahead and leave the track out. Okay, so I'll call this the block spring Earth system. Okay. All right. Did you guys say this right here? Sum of energy initial equals sum of energy final. Did everybody write that? Everybody's got that, right? Okay. If that was an FRQ, I think there's a good chance that that would be a point. Just writing that, I bet they say, oh, yep, 1 point. Okay. All right. Now, what did you guys write for the left side? 1/2 kx squared, right? Oh, I meant to label the spring constant as k, but that's what it would be, right? Okay. And we compressed it distance x. Okay, so that's the source of the energy. Is that right? Right. And energy final. Where did the energy go to? Yep, I had to lift it that height. So mgh. And also, where else? Kinetic, there's your 1/2 mv squared, right? Because these are all energy terms, right? Right, guess that. Right. And there you go, there's your setup. And then if you know all these variables except for one, like v for speed, then you could solve for that. Right, guys, see you can do that. Right, are we good there? Any question? Right. Hey, what if you ever saw an expression that looked like this? Force times distance plus mgh is equal to, wait, never mind, hold on. I think it's something else. Hold on, I had this. Let me start. Right. What if you saw something like this? Kx plus mgh is equal to 0. Right. What if you saw something like that? Guys, there's something fundamentally wrong with this. What is fundamentally wrong with what I wrote? And I haven't even told you, but I don't know, maybe you can make up a question. But what if you wrote that on paper? It would never answer any question because why?
Force versus energy.
Yes, this refers to some kind of force measured in newtons. This refers to some kind of energy measured in joules. Guys, can you add newtons to joules? No, right? Guys, what if I ask you this? Here's a question I haven't pulled out in a long time. What is 3 miles plus 4 gallons? 3 miles plus 4 gallons. That's 7 what? That's not 7 of anything, right? That doesn't even make any sense, right? Okay, so guys, when you're adding terms together, make sure they're all the same unit. Just like this one, they're all energy terms, right? You see that too? All right. Okay. Oh, it's 9:35. They're holding the bell, or they're just not ringing the bells. All right. So I will see you guys tomorrow for one last review.